Hello everyone, I'm Giovanni Quattrocchi and I'm going to present a work about dynamic resource allocation for big data applications. In this work, we target big data batch applications. These applications are usually long-lasting assets, meaning that each application could be executed multiple times with different datasets. Each execution could last several minutes or even hours, and the quality of service is defined as deadlines, where a deadline is the maximum allowed response time for a single execution of the application. These kind of applications are usually executed using a dedicated framework, such as Spark. Spark uses a master workers architecture. In the master, different applications can be scheduled by the user concurrently, and the master also orchestrates the execution of each application in phases. In the workers, the actual computations are executed. In particular, workers use multiple executors to distributedly execute the applications in separated processes. Resource provisioning in Spark can be defined in three different ways. So user can either do nothing and use the default option, which is all the resources are allocated to the first application in the queue. Second, users can configure the system in order to use a specific amount of executors with a specific static allocation of CPU and memory. Third, users can also use a more dynamic and automatic way in which user can set the maximum and the minimum amount of executors to use, and then using timeouts, Spark automatically removes or increases the number of running executors. The problem is that in order to fulfill a given deadline, user must guess the right configuration. In fact, Spark doesn't have any notion of deadlines in its processing model. So the problems are two. First, we need to allocate the minimum amount of resources in order to fulfill the deadline, which means optimize resources. Second is scheduling parallel applications according to the priority, which means we need to take into consideration the resource contention that can happen among different applications running on the same Spark cluster. To do that, we present DinahSpark. So DinahSpark is an extension of Spark based on four levels of control. First, a centralized planning system that exploits profiling data, which are the performance obtained by each application at each phase. And for each phase of the application, DinahSpark computes a local deadline and initial resource allocation using an heuristic. The second phase is the centralized control. So each executor is wrapped onto a container and equipped with a controller. Each controller manages the vertical allocation of CPU cores of each executor. It's control theory based, and the set point is the local deadline. So the goal of the controller is to match the local deadline, while the control variable is the application progress. The allocation is very fast. In fact, the control period is set to be equal to 0.5 seconds. Third level of control is the centralized app scheduling. So on each worker, we can have multiple containers controllers deployed in the same machine. So a supervisor manages the resource contention according to a specified strategy. Supervisor also can accelerate or decelerate applications given the computed allocations. And multiple built-in strategies are available in DinahSpark. Finally, we also take into account the memory management. So in this case, we vertically scaled off-heap memory. And we use off-heap because each executor is a JVM and it's not possible to easily execute heap memory for JVMs. And the memory of running application is shrinked when a new application is scheduled, and on the contrary is expand when an application terminates. And also this layer is based on an heuristic. Finally, in the evaluation, which here is just presented in a very short version, we used 8 benchmark applications and we deployed the system in Azure. And the main metric is the precision, which means how close the response time of each execution meets the defined deadline. And the closer DinahSpark gets to the deadline, the fewer resources it uses, meaning that the resource allocation is optimized. So we tried different deadlines, different datasets, and skew data, and on average, the precision is greater than 98%. This concludes the presentation. Thank you for your attention.